regardless of how one's gaze is cast upon the vast expanses of space, be it with the naked eye, through the shimmering lens of a telescope, or in the deepest thought experiment. This realm always appears boundless and immeasurable. It seems to stretch infinitely in all directions, with no beginning or end, and this is precisely how our mental model, our simplified understanding of the universe, has become deeply ingrained in our consciousness. However, this intuitive model is not necessarily an absolute truth. There exists a fascinating and equally plausible alternative. What if the universe, contrary to our perceptions, is actually finite in size and possesses a distinct, tangible shape? Perhaps the boundless sky we observe is nothing more than a grand cosmic illusion, born from the complex warping of spacetime itself. This idea may seem fantastical, transcending ordinary perception, but it is no less, and perhaps even more, probable than the concept of a boundless universe. A finite universe is one of those astonishing, non-trivial possibilities that intrigue scientists, compelling them to relentlessly seek empirical evidence. And most importantly, unlike the hypothesis of infinity, this scenario is testable. In this discussion, we will delve into the depths of this intriguing mystery, exploring what shapes our universe might take and what methods allow us to uncover its true nature, aiming to definitively resolve one of the most fundamental mysteries of existence. It is important to understand that from the perspective of current observations, the simplest and most obvious explanation remains an infinite universe. After all, we don't see its edges, do we? The speed at which distant galaxies recede from us increases proportionally with distance, creating the impression that this expansion is absolutely homogeneous and uniform at every point in space. This is a natural consequence of an infinite universe, where everything moves uniformly, without the slightest hint of any center around which the expansion might be occurring. Similarly, measurements show that the curvature of space appears perfectly flat and even, as if space itself, were it to be depicted in 2 dimensions, would be an infinite, flawlessly smooth sheet of paper stretching in all directions. More details on what flat universe truly means will be discussed later in this captivating exploration. The main idea is that such a geometrically flat space is a strong indicator of an infinite universe. And frankly, this is perhaps the simplest, yet also the strangest, and possibly even the most boring, of all possible realities. Not only because an all-encompassing, boundless cosmos can evoke a sense of profound loneliness and insignificance, but also because the transition from absolute nothingness to infinity is difficult to comprehend. Infinity implies an infinite amount of matter and energy, which inevitably raises the question, how could something so vast come into existence in the first place? Ultimately, it is conceptually simpler to imagine the creation of something finite, so it is quite natural to seek alternatives to such a scenario, where the universe might be extremely large but still have a finite volume. If it is indeed not much larger than the most distant objects visible to us, the chance of detecting its true shape significantly increases. And here, we are not talking about some physical wall that would serve as the boundary of our imaginary cosmic bubble. In fact, in most cases, scenarios involving a physical boundary of the universe are usually not taken seriously by scientists. Spaces with distinct edges are simply too exotic, raising numerous unanswered questions. What even is this boundary? And what lies beyond it? What happens at the very edge? How would matter behave upon reaching this boundary? Could it cross it? And would the edge alter its fundamental properties? All these questions necessitate overly complex and unsubstantiated assumptions that cannot be confirmed by observations or even theoretical calculations. Modern cosmological models describe the universe as the totality of all that exists within space and time, rather than outside of it. Literally contemplating existence, beyond, requires the creation of entirely new physics. Therefore, a universe limited in volume, that is, a finite space, is indeed considered a serious hypothesis, but typically without any wall to run into. In other words, after an infinite universe, the second most probable and exciting option is a compact finite universe, which, however, has no boundaries. Compact means it is indeed limited in size, and no boundaries implies that it is simply closed in on itself, similar to the surface of an object. This is best illustrated by the example of the Earth's surface. If you continuously travel across the surface of a sphere, you will never find an edge and can walk on it forever, always returning to your starting point. Yet, a sphere, our planet in particular, obviously has a finite area. This example is simple and clear, and incidentally, it demonstrates one of the possible topologies of a universe with positive curvature, namely a sphere. But from a topological perspective, Earth and any other sphere are two-dimensional figures, as we are only talking about their surface. It is this surface that represents the space we live in, and in this example, we would also have to be two-dimensional beings. Therefore, such a spherical model of the universe requires another dimension and represents a three-sphere. But let's not overcomplicate things for now. It should be noted immediately that in the case of a spherical closed universe, there is a theoretical possibility of traveling in one direction and eventually returning to the starting point, much like traveling along the Earth's equator. However, there is a vast number of different topological models, and by no means do all of them allow you to return to your home galaxy, star system, or planet. The universe can possess incredibly complex and diverse topologies, and even in a closed universe, straight-line motion will not always bring you back to your starting point, adding another layer of intrigue to this cosmic enigma. From a purely mathematical perspective, there are countless potential non-trivial configurations of a finite universe where the principles of general relativity are equally applicable. Choosing the single one that best describes reality might seem like an incredibly laborious task. However, fortunately for researchers, there are certain physical characteristics of the universe that allow for a significant narrowing of the list of possible topologies, and the exclusion of the vast majority of them. The most important of these properties is the curvature of space. Since we have already touched upon this term, it is necessary to strictly differentiate between the concept of curvature or geometry of space and its topology. Topology refers to the global structure of the universe and how it is interconnected across the entire cosmos, whereas the curvature of space is the degree of its local deformation, that is, how much space itself is warped at a particular point. Within his general theory of relativity, Albert Einstein demonstrated that space is deformed by massive bodies, giving rise to gravitational interaction. Consequently, depending on the total density of matter and energy filling the cosmos, space on the scale of the entire universe can possess a certain curvature. Essentially, if astronomers can grasp spatial geometry and understand how it curves, they can draw informed conclusions about the possible topologies consistent with such a cosmos. Cosmologists have some luck in this matter, as the observed appearance of the universe allows the number of possible geometries to be reduced to just 3. This is evidenced by the cosmic microwave background (CMB) radiation, the first radiation released from the primordial plasma of the Big Bang, just 380,000 years after the very beginning of cosmic evolution. A key characteristic of this radiation is its striking uniformity. It has an almost identical temperature in all directions, almost identical, as the negligible fluctuations, represented as spots on maps, do not exceed 0.00001 Kelvin. Similarly, the study of distant galactic structures in the local universe and their vast clusters demonstrates an almost uniform distribution of matter. The universe we are able to observe appears virtually identical in all directions. Such exceptional homogeneity is possible only in a space whose curvature is also uniform and remains constant regardless of spatial coordinates and orientation. Thus, only 3 types of geometries fit this description: spherical geometry with positive spatial curvature, geometry with zero curvature, also called Euclidean or flat, and hyperbolic geometry with negative spatial curvature. This topic is a subject of independent scientific inquiry, but let's briefly consider what this means. At least one of these 3 names should be familiar, as Euclidean geometry is what is studied in school. This is space with zero curvature, i.e., a standard flat surface on which students solve geometry problems, constructing various geometric figures and studying their characteristics. In such a space, the sum of the angles of any triangle invariably totals 180 degrees, parallel lines always remain parallel, and the area of a circle is pi r superscript 2. This is what humanity is accustomed to in everyday life. However, if the task were not to complete homework on a sheet of paper, but, say, on the surface of a globe, with the need to draw a triangle on it, the familiar Euclidean geometry would lose its applicability. The sum of the angles of such a triangle would turn out to be greater than 180 degrees, because the triangle is formed by segments of arcs, which are geodesic lines, shortest distances, between points on a sphere. Due to the curvature of the surface, these arcs bend, and the angles between them increase, and consequently, their sum also increases. This is an example of space with positive curvature, also called a closed universe. Another option is a space where, during movement from one point to another, the effective space curvature leads to a negative difference, meaning the sum of the angles of a triangle will be less than 180 degrees. This is hyperbolic geometry with negative curvature, which corresponds to a space that takes on a shape resembling a saddle-like surface or, for instance, potato chips. This type of universe is often referred to as open. In general, it should be understood that these three possibilities for space curvature are analogous to how massive stars deform the space-time continuum around them. But in this case, the curvature of the universe is due to the cumulative mass of all the matter and energy contained within it. If this mass exceeds a certain threshold, space acquires a positive curvature, and if it is less, it will curve negatively. So, what is the actual geometry of our cosmos? Surprisingly, to determine it, cosmologists resort to the method of constructing large-scale triangles and measuring their angles. However, the vertices of these triangles are the most distant cosmic structures, such as individual galaxies or their vast clusters. The larger the triangle that can be drawn, the better the spatial geometry will reveal its true characteristics. Therefore, it is not surprising that the most effective method for its determination is the study of the cosmic microwave background (CMB) radiation. It represents the oldest and most distant imprint of matter in the universe, both in time and space. The appearance and shape of temperature fluctuations, as well as the angular size of primordial acoustic waves, are directly affected by the curvature of space. In other words, it is possible to model what the CMB map might look like for each of the three possible curvature scenarios, and thereby determine which one most accurately matches observational data. Some aspects have already been discussed in previous conversations, but many key and exciting features of the CMB are yet to be revealed in future publications. For now, it is worth noting that extensive cosmological data convincingly indicate the existence of our universe with a remarkably flat geometry, with an error margin of less than 1%. In other words, the total mass of all matter and energy filling its expanses is neither excessively large nor abnormally small. It is as if it is perfectly balanced and harmonious. Such conclusions are, of course, based on careful analysis of the part of the universe accessible to our observations. Thus, while some may ironically mock proponents of a flat Earth, we actually inhabit a universe that is indeed flat, albeit in a completely different interpretation than that imagined by the unfortunate adherents of the aforementioned misconception. Overall, the phrase flat universe can seem somewhat disheartening and tends to confuse rather than clarify the phenomenon. For this reason, in further discussions, it will be preferable to use the term Euclidean space, which accurately describes flat geometry. Intuitively, it seems that the simplest embodiment of a flat three-dimensional structure is the familiar infinite space, the way we usually imagine it. It appears perfectly even, homogeneous in all directions, and simply boundless, extending everywhere. However, one should not be deceived. This representation does not necessarily reflect the true picture of the universe. In reality, there are topologies of universes that, despite their limited size, are fully consistent with Euclidean geometry. This means that such universes are closed in on themselves, yet the sum of the angles of any triangle within them still totals 180 degrees. Two parallel lines invariably remain parallel, and the fundamental principles of general relativity function flawlessly. And fortunately for cosmologists, the number of such topologies is small. There are only 18, which significantly increases the chances of discovering the true structure of the universe. Among these 18 topologies, the simplest, most logical, and the first that comes to mind, as well as the easiest to explain and understand, is the figure known as a donut, bagel, ring, or, in mathematical terms, a torus. Of course, this is not a literal torus, as it lacks one dimension for an adequate representation of three-dimensional space, but for clarity and simplification, it is excellent. The reason why the torus is most often visualized and constantly appears in discussions about the shape of the universe lies precisely in its simplicity and accessibility for perception, not necessarily because it represents the most probable model for the real cosmos. But let's consider everything in order. Looking at this object, it is quite difficult to imagine that the universe, or more precisely, Euclidean space, could be like this, because its surface looks uneven and curved. However, it is extremely important to understand that a torus is actually nothing more than flat space, essentially, an ordinary sheet of flat paper that is closed in on itself. To grasp this concept, let's imagine a two-dimensional plane, for example, a regular square or rectangle, which mathematicians call the fundamental domain of a torus. This rectangle will serve as a visual model of our flat universe, but only in two dimensions, similar to the example of the Earth's surface. Accordingly, the inhabitants of this simplified universe are also two-dimensional beings, such as their peculiar fate. Not yet entirely obvious, but an extremely important characteristic of this hypothetical universe is its closed nature. For a hypothetical rocket that we mentally sent on a journey, this means that upon crossing one of the edges of the sheet, it instantly reappears on the opposite side. It doesn't matter which edge it is directed towards, the rocket will always return from the opposite side. Yes, such behavior might seem unrealistic, as if the rocket is teleporting. Therefore, to ensure continuous motion in a closed space, one must mentally glue together two opposite edges. Now, this looks much more plausible, as the rocket moves along a continuous closed trajectory, at least in one direction. For this property to extend to all directions, the remaining two sides of the resulting cylinder must also be glued together. And once this is done, we get a torus. Now, wherever the rocket's flight is directed, it will always move in a closed space, and its straight-line motion will invariably bring it back to the starting point. This is truly remarkable. Thus, a rectangle can be rolled up in such a way that it forms a donut. In doing so, two parallel lines will maintain their parallelism, and general relativity will function fully. However, it should be noted that this is only the local geometry of the torus, as the sum of the angles of a triangle can change due to curvatures in specific locations, rather than due to the overall curvature of the space itself. Unlike a sphere, there is no center or poles here. Globally, the torus is actually an excellent example of truly flat space. Similar to the real universe, it lacks global curvature, although local irregularities may be present. Consequently, a two-dimensional flat, or Euclidean, torus represents a very worthy alternative to the concept of an infinite cosmos. Nevertheless, it must be acknowledged that the experience of existing in such a universe would be significantly different from our own, and it is extremely important to understand and realize these differences to more deeply comprehend what kind of universe we actually inhabit. Thus, although to an external observer the rocket's path appears circular, for two-dimensional beings living on the surface of a torus, it would be a perfectly straight line. They simply move in a straight line in their flat space and do not perceive any changes in direction, because there are no such changes. Now, this applies not only to the rocket but also to light, as photons also follow similar trajectories. They travel strictly straight. This circumstance leads to a very curious conclusion. If photons in a closed universe travel along closed trajectories, then in such a universe, if one looks far enough, one can literally see the back of their own head. This can be compared to the unusual experience of walking while constantly observing oneself from behind, a very strange sensation. In other words, imagine leaving one room and entering the next, which strikingly resembles the previous one, but is actually the same space you just exited, only from a different side. This is how a closed universe is structured. If such a universe turns out to be sufficiently compact, one could literally behold countless reflections of oneself, and from all sides, not only front and back, but also right and left. This phenomenon is strikingly similar to the effect of a mirror room. Now that this concept is understood, we can finally leave the two-dimensional analogy, that is, a universe existing on the surface of a two-dimensional torus, and move to the next level of understanding, attempting to visualize a three-dimensional torus, or three-torus. However hard one tries, the human mind cannot imagine what a three-torus would look like from the outside. It cannot be depicted on paper, and it can only be described using mathematical formulas. Fortunately, however, one can try to imagine what it means to exist inside such a universe. Just as life in a two-dimensional torus resembled existence in an infinite array of identical two-dimensional rooms, life in a three-torus is analogous to being in an infinite three-dimensional array of cubic spaces. In such a universe, one could literally see an infinite number of their own copies, front, back, left, right, top, and bottom. Beyond these nearest copies, others, even more distant, would be visible, as far as visual acuity and the finite speed of light allow. But these copies are not separate entities. They are the observer themselves, because the photons emanating from them travel along closed trajectories and invariably return. Of course, this may seem unreal, because in our real universe, we do not observe countless reflections of ourselves or our planet. However, the universe we live in, even if it is limited in volume, is significantly larger than the imagined cube we used for the analogy. Perhaps we simply have not yet detected signs of this space closing in on itself, because the point where it folds back on itself is too far away. But no one will deny that astronomers are actively searching for these signs. We will return to this question later. It is important to emphasize now that such a closed universe is also consistent with the expansion of space that astronomers observe. If the fundamental domain, that is, the hypothetical cube we are in, expands, then the space it creates expands with it. Every point of the expanding space moves away from another, which is precisely what is observed. In other words, the overall effect will be the same as for a boundless universe that has no volume limitations. We hope that we have succeeded in conveying an understanding of what life would be like in a three-torus universe. If so, then other, somewhat more complex topologies of Euclidean space are also comprehensible, as they often represent merely certain variations of the three-torus. For example, some topologies also use a cube as the fundamental domain, but the faces of the cube will be connected with a certain twist. Roughly speaking, upon leaving such a cube from one side, the observer would return from the opposite side, but at an angle of 180 degrees. Another variation of this space assumes a rotation angle of 90 degrees. In other words, one would still see countless copies of themselves, but they would have different orientations. Overall, this is still a three-torus, although it looks a bit more complex. Literally, it's a slightly twisted three-torus. The picture is somewhat complicated by a space that uses not a cube as its fundamental domain, but another figure, a hexagonal prism. Yes, this is a less familiar object to us, but it also fits well into flat Euclidean space. To begin, let's consider its two-dimensional analog, this hexagon. If you try to connect two of its faces, you again get a cylinder, but with so-called skewed cuts. That is, the two planes will not be parallel and will be inclined at a different angle to the cylindrical surface. Now, if you connect these two planes to each other, they can also form a torus. But for this, they need to be rotated slightly relative to each other. Fortunately, in topology, objects are treated as if they are made of rubber, so nothing prevents them from being rotated and stretched as desired. The main thing is not to violate their continuous structure. Thus, the two planes indeed join, forming nothing other than a Euclidean torus. Of course, the three-dimensional analog of such a universe will look somewhat more daunting, as it is no longer a cube but a prism, but in general, it can also be understood. In it, upon crossing one of the faces, the observer will appear from the opposite side, but the hypothetical front face, which has 6 angles, will be rotated by 120 degrees relative to the hypothetical back face. That is, upon crossing one of them, one will return at an angle of 120 degrees. Another variant of this topology shows a similar picture, but the rotation will be half as much, 60 degrees. Perhaps the most challenging concept to grasp is the topology of the double cube space, which features an unusual gluing scheme where all faces are identified with rotation. Without delving into details, suffice it to say that an observer's copies would appear everywhere, with highly varied orientations. There are also 4 possible topologies for infinite space, the simplest of which is well known to humanity: Euclidean 3-dimensional space, where 3 axes extend to infinity. This is how the universe is currently understood in modern scientific thought. It exhibits no self-copies of objects and extends far beyond our observational horizon. Another 8 topologies on this list are non-orientable, meaning it's impossible to choose a single, consistent orientation for all closed loops within such a space. For instance, if a traveler were to leave Earth in such a space and then return, everything around them would appear in mirror image. What was on the left would be on the right, and vice versa. Clocks would run counterclockwise. Surface inscriptions would look mirrored, and people's hearts would be on their right side. Notably, the returning traveler themselves would also appear mirrored to those on Earth. While intriguing, this concept is perceived as somewhat strange and, for this reason, rarely receives serious attention in scientific circles. 10 other orientable topologies, including the so-called tri-torus, and its many variations, are considered a more favorable alternative to the idea of an infinite universe. A natural question arises: how can we possibly discern which universe we actually inhabit? The simplest approach assumes the universe is in fact a tri-torus with a radius, say, less than 5 billion light-years. In such a scenario, light rays would have traversed it 3 times, meaning every cosmic object, be it an individual galaxy or a galaxy cluster, should appear 3 times in the sky, like a ghostly apparition observed in different parts of space. This implies that, theoretically, such a universe model could indeed be verified through observations. It would only require detecting an exact copy of a galaxy, for instance, a repetition of the Milky Way. Of course, we don't know the exact appearance of our own galaxy in perfect detail, but that's not the main issue here. A far more serious obstacle is the finite speed of light. Even if a duplicate of the Milky Way or Andromeda were found 5 billion light-years away, these galaxies would look completely different from how they appear today. They would be captured at earlier stages of their evolutionary development. We might simply not recognize ourselves, or even Andromeda, because they would appear significantly younger. The very nature of light emission prevents us from pursuing this path. Furthermore, these copies would appear in different directions, possessing varying luminosities and orientations. How could they possibly be identified under such conditions? It seems virtually impossible. The universe could literally be extremely compact, even smaller than we imagine, yet its intricate topology might cause objects to appear evolutionarily distinct, with diverse shapes and positions, creating the impression that they are entirely different objects located at vast distances from us. This could be a grand, astonishing topological illusion, virtually indistinguishable from a universe with infinite space. Currently, based on available observations, we can conclude that the universe is unlikely to be highly compact, as we would still likely detect copies of known galaxy clusters, even if they had different orientations. However, it remains possible that the most distant red galaxies are merely phantoms of modern ones. And while this may sound strange and somewhat fantastical, it cannot yet be definitively ruled out. Despite the apparent complexity of the task, certain possibilities exist for testing the universe for evidence of finiteness. If the question arose as to where such traces should be sought, many would likely guess the cosmic microwave background (CMB) radiation is a suitable tool for finding topological signatures, as it is nothing less than a unique map of the early universe, captured in subtle temperature fluctuations. If the universe indeed possesses a non-trivial topological structure that creates copies in certain directions, and if this topology does not exceed the scale of the observable universe, then these copies should imprint themselves on this map. Simply put, one needs to look for identical patterns, that is, repeating patterns of temperature fluctuations. This task is certainly not simple, as temperature variations are inherently random and extremely subtle, and some topologies can shift or even invert these copies. Each of the 18 flat topologies generates an infinite number of variations for the CMB map, and analyzing all these variations poses an enormous challenge. Currently, there is an active search for statistical patterns within the minuscule temperature fluctuations, with researchers tirelessly checking whether these variations are random or not. Additionally, scientists continue to inventory all matter within the observable cosmic volume. Specifically, space telescopes like Euclid and Nancy Grace Roman will be the next significant steps in this direction. The Vera C. Rubin Observatory, currently under construction on Earth, is also expected to make a substantial contribution to these studies. Consequently, by combining data from all available observations with information obtained from the CMB, there may be a chance to uncover a hint of the universe's topological structure, as its influence extends throughout the cosmos. Of course, it's also possible that its fundamental scale might be too vast for us to observe any copies. Perhaps the boundaries of our hypothetical cube lie beyond the cosmological horizon, and photons from those regions will never reach us throughout the universe's multi-billion-year history. In other words, the loops along which photons travel might be so immense that light will never reach us due to a fundamental characteristic of space: its continuous expansion. From the author's perspective, this latter option is favored, as the concept of infinity appears highly unusual and even illogical in all its manifestations. A natural question arises: how can something boundless even originate? What physical mechanism could possibly facilitate the formation of such a phenomenon? For the author, infinity is more a notion perceived as illusory, devoid of true reality. Nevertheless, it must be acknowledged that with the current level of scientific development, and considering modern cosmological data, the observable universe presents itself precisely in this manner.